In the second lecture on isomorphisms, we're going to get more precise and rigorous here. So let's try to get the definition right. Okay, so let's recall the rough notion of isomorphism that we mapped out in the previous lecture. We're trying to get at the fact that we want to say that the group structure of G is identical to the group structure of L, even though they're technically different groups with different elements and different operations. So what kind of properties do we expect such an isomorphism to have? So I'm trying to motivate the definition of isomorphism the right way. We've yet to define it mathematically, but I'm trying to motivate it here. So let's think about this a little bit. So the first thing to notice is there is a really subtle ambiguity in how I described using the table for G to replicate the table for L via this renaming function alpha that I described in the last lecture. Okay? Let me give you an example of what I mean by this. Suppose we want to consider, in the table for G, we had B times C equals A. You can look it up and see that I'm right, okay? B times C is A. And that is supposed to translate to something over in the group L, okay? So let me remind you of how alpha acted. Here's the renaming scheme for alpha. E goes to 1, A goes to W, B goes to pi, and C goes to heart, okay? So according to this translation here, the equation B times C equals A, which was true in G, well, that's supposed to, it should become, well, what is B? Pi. What is C? Heart. And what is A? W. So B times C equals A, which is an equation in G, that is supposed to become pi operate heart equals W in L. Okay? But however, there are two ways to do this, and those two ways, they might conflict with each other, which would be bad. Okay? Let's see how you could do this in two different ways. First, what you could do, you could look up the verdict for B times C in the G table. If you look up what B times C is, you know that it's A. So what should that convert to over in L? Well, what's alpha of A? Well, it's W. So the verdict ought to be W. All right, that's one answer for what pi operate heart should be is W. You look up B times C, notice what it is, and then map it over to L and get W. But you could also do the vice versa. Why couldn't you map B and C over to L first and then operate in L and see what you get? Okay, well, what is B over in L? It's pi. What is C over in L? It's heart. And what is pi operate heart? Well, it's W. And of course, notice that's the same thing you get this way. And you should always, always, always ask to have that sort of consistency, okay? So this function alpha is nice in that it did the right thing. No matter how you did it, you got the right answer of W. And if you look at these two different methods, the first method did alpha of B star C, and the second method did alpha B diamond alpha C. And of course, we want this right here to happen for all choices of inputs, not just B and C. In other words, we must demand that alpha be a homomorphism. This is the rule if you demand this for all the elements, that alpha be a homomorphism. Okay? That's step one. Our beloved isomorphism must be required to be a homomorphism. Okay? Moreover, alpha should be an honest relabeling of the elements of G as elements of L. So each element of G should receive only one new name. That just means alpha is a function. It would be bad if I said that E is going to go to 1, but E is also going to go to W. Then whenever you saw an E in the table, how would you replace it? By a 1 or by a W? By both? So alpha's got to be a function. All right, it's got to be a function. At the same time, the vice versa should happen. Every element of L should come about from only one element of G, right? It would be bad if E and A both went to 1. If E and A both went to 1, then you're going to violate the Latin square condition in the group table for L, because you're going to have every row having one E and one A. And now in the new table for L, if E and A both go to 1, both of those E and A become a 1, and that's going to have two 1s in the same row. So you can't have that and have a group. So each element of L should come from a unique element of G. And that just says that this function alpha has to be 1 to 1, right? Otherwise, you'd have two different elements getting relabeled as one element. And that would create those conflicts in the translation of the table from G to L. Can't have that. So alpha has to be 1 to 1. At the same time, you want to make sure that every element of L came from some element of G. Okay? Suppose the element pi in L did not come from anybody from G. then when you make the table for L out of the table for G, pi is not going to show up, right? Because pi didn't come from anybody. And pi is an essential element of the group L. It needs to be in the table, and that can't be allowed. So alpha must also be onto. So we just argue that alpha needs to be onto, and so if you look at what we said here, our function alpha must be a homomorphism, and it must be one-to-one, and it must be onto, and this gives you the correct definition of isomorphism. So let G and L be groups. An isomorphism, alpha from G to L, is a bijective, so one-to-one and onto, homomorphism. When such an isomorphism exists, we say that G is isomorphic to L, and we write it this way: G is isomorphic to L. That's the correct definition. So the philosophy is, when alpha from G to L is an iso, G and L have the same algebraic structure, and we'll get into this more in future lectures, okay? But the point is that the function alpha faithfully recreates the group structure of L out of the group data for G. Now, of course, G and L could be different. They could have different names of their objects. They could have different names in their operations, but alpha doesn't care. It's a faithful relabeling of everything, and those differences have no impact on the algebraic data, okay? So the idea is that this is supposed to capture the notion of saying G and L are structurally the same, right? They're algebraically the same. And whenever you have something being the same, there should be something like an equivalence relation lying around, and there is. Okay, so it turns out that the isomorphism relation is an equivalence on groups. In other words, every group is always isomorphic to itself. That follows because the identity function from G to G, you can check, meets the definition of an isomorphism. So everything is the same as itself. Well, that makes sense. You want to be the same as yourself. It also has symmetry. If G is isomorphic to L, then L is also isomorphic to G. Well, that makes sense too. If G and L are algebraically the same, it ought to be true that L and G are algebraically the same, right? If I can make L from the table of G, I should be able to reverse that and make G out of the table for L. And sure enough, isomorphism is a symmetric relation. Here's the argument. Suppose alpha from G to L is an isomorphism. That says G is iso to L, right? I got to somehow go the other way around, okay? Well, alpha is bijective, and so the inverse function exists and is also bijective. So alpha inverse goes from L to G, and that's a bijection because its inverse is alpha, so it's invertible. You can then check, this is not automatic, but it is a really good exercise. You should then check that alpha inverse is a homomorphism because alpha was, and therefore alpha inverse is a homomorphism that is also one-to-one and onto, and therefore it qualifies as an isomorphism. That says that L is isomorphic to G, right? So this relation is symmetric. Likewise, the isomorphism relation is transitive. If G is iso to L and if L is iso to M, then G must be iso to M. Okay, here's the proof. Well, if G is iso to L, that means you have an isomorphism alpha that runs from G to L. If L is isomorphic to M, there must be an isomorphism, call it beta, that moves from L to M. Well, if I have a function from G to L and another one from L to M, I can compose them and get a new function from G to M. That function is called beta compose alpha. But you already know that the composition of two bijections is a bijection, so therefore beta O alpha is a bijection. And it's also not hard to check that the composition of two homomorphisms is once again a homomorphism. So beta O alpha is a homomorphism, but it's also a bijection, and so it is an isomorphism, and that proves that G is isomorphic to M. So it's transitive, right? So as just one little example here, look at the groups G and L from the previous handout. We've already proven they're isomorphic because alpha gives you the isomorphism, right? The alpha from the previous handout. But it's not hard to see that G is isomorphic to Z4, right? It's actually cyclic order 4. And here's an isomorphism you can build from G to Z4. Make E0, A1, B2, and C3. So G is iso to Z4, right? But L is also isomorphic to Z4 because G and L are isomorphic, and that's transitivity. So now I know that L is also isomorphic to Z4. And so all three of those groups are actually the same. Now the same should be in quotes. It's the same algebraically. Yes, they're all different. But those differences I don't care about because they are, from the point of view of group theory, they are all algebraically the same. They are all isomorphic. Okay? Let's take a break and we'll look at the fundamental problem regarding isomorphisms in group theory.